In previous lecture, we studied a solution method of the Hills equation that was based on the matrices. Now we will see there is another way of solving the Hills equation, and we will see in this lecture. What we did earlier, actually we reduced this equation to simple harmonic oscillator equation by keeping k constant in different elements. Means we divided complete optics in pieces. One piece may be of the one magnet, and inside that piece k is constant, and we solve that equation just like the simple harmonic oscillator equation. This method, which leads to matrices, also known as piecewise solution of the Hills equation. Again, we can see that how the k varies. It is just a repetition of something which we learned earlier, but repetition is sometimes better to learn in effectively. So suppose this is a bending magnet, and we are plotting in the bottom graph k for this optics. So in certain dipole magnet, k may be 0. What is that case in which a dipole magnet can produce k0? The first very case is it should not have the gradient. And then in the last example of last lecture, we have seen that parallel edge magnet acts just like the drift. So if this is a parallel edge magnet without any gradient, then k will be 0. So assume that this kind of magnet is this, so k is equal to 0. Now there is a focusing quadrupole. Again, remember, this is a convention. When we say focusing quadrupole, means it is focusing in the horizontal plane. So k will be high here, and it is again a convention that we make k positive for the focusing quadrupole, and height of this k is just the showing the magnitude of k for this quadrupole magnet. So k will be just like here inside this quadrupole, k has certain constant flow. Then again drift, so k will be 0. And then there is a defocusing quadrupole in this example. So k will be plotted on the negative side, and height of this plot is just similar to the magnitude of this defocusing quadrupole strength. Then there is again drift space, so k is 0. Now here in this bending magnet, there may be some k, means it may have some gradient, or it is not a parallel edge magnet, so some k is there. And you can see that direction of k is like the focusing quadrupole, means it is focusing in the horizontal, maybe a sector magnet like that kind of. However, you can see that k is lower than quadrupole, because this provides a weak focusing and quadrupole provides a strong focusing. So in general, in usually optics of charged particles, the focusing effect of the dipole magnet is weaker than or not much significant when compared to the quadrupole. And again there may be a quadrupole, so again the k rises to this value, and again a drift space kc. So such kind of function k may be defined by such type of function of s, and in each piece we solved the equation of motion and glued the solution. This is known as piecewise solution. Now we see we can plot various trajectories. Various trajectories means trajectories associated with different initial conditions very easily using this piecewise solution or matrices. It is just an example in which you can see that the first element, magnetic element, is defocusing quadrupole, second is focusing quadrupole, and third is again a defocusing quadrupole, and fourth is a focusing. So this provides overall focusing if we choose carefully the strength of this quadrupole as well as distance between these four. So how the matrices can be used to produce the trajectories within different initial condition, you will see in this video. So now as this trajectory reaches to this magnet, all defocuses, and then it focuses means coming, these are coming towards the design trajectory. Again, this is a defocusing magnet, the effect will be such kind of thing, and lastly you will have a focusing magnet. So all the trajectories again are coming towards the design trajectory. So you have an overall focusing solution for this case. Now, is there any way to solve the Hill's equation really keeping k as a function of s? Is there any mathematical tool in which we need not to break the optics in pieces and for each optics we solve differently? Yes, definitely we have. Now suppose this is the picture of one of the trajectories which we plotted in the movie. Now you can see that this trajectory is going upside due to defocusing magnet, and again due to focusing it is coming towards the design trajectory, and again this defocusing magnet produces some effect of defocusing, so angle with respect to design trajectory has been increased, and again a focusing. So overall, under the action of defocusing and focusing effect due to these quadrupole magnets, the trajectory is seeing some kind of oscillatory behavior along the design trajectory. Means this trajectory shows some kind of oscillatory behavior, and you can see in each trajectory of that movie that some kind of oscillatory nature is there. Means this focusing and defocusing effect actually produces some oscillation in the trajectories. These oscillations are known as beta-tron oscillations, and transverse beam dynamics is actually the studies of beta-tron oscillations. So now we know that there will be some oscillatory type solution for the Hill's equation. Definitely these oscillations are not very simple. You cannot represent it by single sinusoidal or like that. So this may be because of the S dependence of K. S dependence of K means if you will choose S, say S is equal to S1, you will get different K means different wavelength locally here. And if you will put S is equal to S2, you will get a different wavelength locally here. It means amplitude will also be a function of S. Keeping these two things in mind, one, oscillatory solution, and second, the amplitude may be the function of S, we can have a trial solution of this equation. So we can write down the trial solution like A B as a function of S, cos phi S and phi C. Now because this is a second order differential equation, we require at least two constant of motion. That's why this A and phi 0 serve that purpose. So A and phi 0 can be obtained using the initial conditions. Now because this is our trial solution, so what should be the nature of B and phi? If we want to know that, we will put this trial solution into the Hill's equation. So for doing this thing, we have to obtain the x double prime, means second derivative of x with respect to s. So differentiate x with respect to s, we will get, now here amplitude itself is a function of s, so we have differentiation of this amplitude also. So ab prime s cos phi s plus phi naught minus ab, this is the differentiation of the cosine term, so cos phi s plus phi naught into phi. This is the differentiation of phi with respect to s. We don't know what is the dependence of phi on the s. We will know by putting this term into the Hill's equation. So just we are putting 5 prime s here. Again differentiating, so we will get x double prime, this equation, a b prime double prime cos. I have omitted here the writing down again and again this s in the bracket. Keep it in mind that these quantities have dependence on x. So this a b double prime cosine term minus a b prime sine term with phi prime, and all these terms, when you differentiate these two terms, you will get this equation. This is an easy thing which you can do. Now we have x double prime, and we also know what is our trial solution x. So x double prime plus kx is equal to 0. This is the Hill's equation. So using these two equations, we can put into the Hill's equation. So we will get these when we will put these terms in the Hill's equation. This is the expression which we get. Now you can see here that this is true. Phi is a function of s. So this is true for everywhere. Whatever is the s, it should be the true, because Hill's equation is valid everywhere. So cosine and sine coefficient should separately be 0 to satisfy this equation. So let us do that. So here we collect the term with sine. So this is the first term with sine, and this is the second term with sine. So the coefficient of sine is here is minus twice a b prime phi prime minus a b phi double prime is 0. So this a cancels out. So we get, and minus sign also you can make it or plus, 2b prime phi prime plus b phi double prime is 0. This is the equation we can. Now we want this equation can give you the relation between the amplitude and phase. B is the amplitude part which depends on the s, and phi is the phase of those betatron oscillations. So this equation actually relates amplitude with phase. If we multiply this equation again with b, it becomes perfect differential. Now you can see that this is a perfect differential, and you differentiate it b square phi prime, you will get the above equation. So this is the perfect differential of this b square phi prime. If you will differentiate it, you will get 2b prime phi prime plus b square phi double, which is the above. So now differentiation of b square phi prime is 0. Means this term which is written inside the bracket must be a constant. So take the constant as 1. So phi prime is equal to 1 by b square. Phi prime means you are writing it as d phi by ds is equal to 1 by b square. Means how much phase advances per unit length. This is encompasses in 1 by b square. So instead of a square, if we have simple term beta, I replace b square by beta. So phi prime is 1 by beta. So we have a simple relationship and simple interpretation of this beta. This beta is now, you can say d phi by ds is equal to 1 by beta. So beta actually is the length of the optics for unit phase advance. So beta has a meaningful thing. It is the length of the optics equal to the length of the optics in which betatron phase advances by unit. So here you can see that in if you will calculate phase, it will comes out to be ds by beta. So this is a bit different relation than the simple harmonic oscillator. In simple harmonic oscillator, what you have? Phi SHM is equal to omega t. So phi SHM varies linearly with the independent parameter t. Phi is directly proportional to t, but in the case of beta tone oscillation, it is not so. Phi varies with integration of ds by beta. So it has a complicated relation with independent parameter, and visualization is a tricky. In the case of simple harmonic oscillator, the visualization of phase is quite easier. Here it is a quite tricky. Now in the solution, we can write down at the place of b, which was our trial solution, root beta using this relation. So our solution will be a root beta cos phi plus cos phi naught, and this phi s is basically this. So our whole solution will be in the form of beta. Now as we have b root beta, so b prime will be this quantity. This is just the differentiation of beta and d beta by ds, and double derivative of b will be like this. So now if we make the coefficient of the cosine term 0, we'll get the second equation. This equation was obtained using the coefficient of sine term equal to 0. So in this case, we will get the equation of beta. And this is the equation of beta, how it varies with s. This is a bit complicated. However, in later chapters, you will see that it can be reduced down to very simple form. So right now, we will not talk about this equation anymore in this lecture. Now, because our solution is a root beta cos phi plus chi naught, we can calculate x prime also very easily. Now here you can see the amplitude part beta has s dependence. So when we differentiate with s, beta has to be differentiated. So this is a 1 upon 2 root beta is the differentiation of root beta, and d beta by d is there, cos as it is, and now root beta as it is and cos has been differentiated, sin phi plus phi, and then d phi by ds. Now d phi by ds we know this is a 1 by beta. Now what we are doing, what we are trying to do, actually we have x is equal to x upon root beta. If we write down, this will be a cos phi, just like the simple harmonic oscillator. And in the case of simple harmonic oscillator, if we differentiate x, we get the velocity. In that case, velocity is also omega a sin phi with minus sign. So can we get some form of differentiation of x similarly? So we are trying to do that. So if this a root beta here cos phi plus phi naught can be put in the form of x upon a root beta in this equation, and when we put x upon a root beta at the place of cos a phi, we will have only sine term in the equation. This a and a will be cancelled out. So finally you will get x prime beta minus half beta prime x is equal to minus a root beta sine phi plus phi. This is exactly what we wanted. Now right hand side contains only sine term, and here right side contains only cos term. I want to put one thing here. In the case of simple harmonic oscillator, we have x is equal to a cos omega t. So if we differentiate it, means we calculate x dot. When I am using the dot, it means it is a d by dt. When I am using the prime, it means it is d by ds. So x dot will be equal to minus omega a sine omega. Now from this you can get x upon a is equal to cos omega. And from here you can write down x dot upon omega a is equal to sine omega. So using these relations you can get x by a square plus x dot upon omega a square is equal to 1. So in coordinates x and velocity, you get an ellipse in the case of simple harmonic oscillator. Can we get such kind of any curve in the case of Betatron oscillations? We are trying to do that. That's why first term we obtained x is equal to a root beta cos phi, and now some variable combination we want in the form of something into sin phi. If we have obtained this relation, that something into sin phi. So now we square and add, we can get such kind of solution which we obtained in the case of simple harmonic oscillator. However, here you can see that it involves d beta by dx, d beta by dx, and it is with minus half scale. Let us define this is a new variable. Say this is alpha. So now our equation become x prime beta plus alpha x is equal to a root beta sine phi, and our displacement is x is equal to a root beta cos phi. So now we have a root beta cos phi and here a root beta sine phi. So if we square it and add it, we can get here 1, and our equation will be like this: x square, I have done the square of the first LHS term, the second LHS term is also has been squared, it will be equal to a square beta. The face part has been removed because of the cos square phi plus sine square phi. So now we open this bracket, so this will be 1 plus alpha square x square, and rearranging the terms, putting together the terms with x square and x prime and x prime is equal to a square beta. So we here a was the constant. We took the amplitude as a root beta, in which beta has the s dependence while a is the constant. So if we divide this equation by beta, then in RHS we will get a constant quantity. Let us do that. So this will be 1 plus alpha square by beta. Here beta will be cancelled out and this will be cancelled and this. So 1 plus alpha square by beta, say this is another variable, namely gamma. So we have now 3 parameters. One is the beta, which defines amplitude at a particular location of S. Then we have differentiation of beta with respect to S, and we relate it with a new parameter alpha, and now alpha and beta combined gives you a new parameter gamma. So definitely we have 3 parameters, but 2 are of these independent. Third can be calculated using the values of 2. So there are basically 2 independent parameters which we have introduced. Now the above equation becomes gamma x square plus twice alpha x prime plus beta x prime square is equal to a square. Now you can see one thing here, that left part contains gamma alpha beta. This beta basically is a function of S. Alpha, because it is a differentiation of beta, it is again a function of S. And gamma, it is also a function of S. So in LHS part of this equation, we have 3 parameters which have S dependence. And also we have x and x prime, which is the coordinate of any particle's trajectory along S. It also varies with S. So LHS part is a function of S, while the RHS is a constant. Means the combination of such S dependence part makes a constant. Means we have found the invariant of the motion. It is just like that in the course of mechanics. You find that energy is the invariant of motion. Here we find another invariant of motion. This is the combination of these. In case of energy, you have x and px. These two are variable and that vary with the time in any dynamical system. But the combination of potential energy and kinetic energy remains constant in the case of conservative system. Similarly, here in LHS part, we have S dependence terms. The combination of these terms gives a constant. So this is the invariant of motion.